Hello everyone and welcome to today's webinar, Ensuring Safety in Syrup Product Detection of Diethylene Glycol and Ethylene Glycol by HPTLC. My name is Tin, I'm the Chief Scientific Officer at CAMAG and I'm joined by my colleague and co-presenter Sonia. Today we will take you through the simple, practical and robust method to detect two hazardous contaminants, DEG and EG, using high-performance thin-layer chromatography. Unfortunately, DEG and EG contamination continues to be a major public health concern. In the past few years, as mentioned here in BBC or several local newspapers, we've seen tragic cases of child deaths linked to contaminated syrup, for example in Indonesia or in Gambia. This toxic glycol can be present in excipient as impurities or can be intentionally added due to cost, often going unnoticed without effective screening methods. Chemically, DEG and EG are diol. They are colorless, sweet-tasting, and absorb moisture, which make them easy to confuse with glycerin or propylene glycol. Some suppliers may use them to reduce cost, and they may also appear as impurities during excipient production. Both are toxic even at low levels. That's why their detection is critical in finished products, especially in syrup formulation meant for children. DEG and EG contamination was first identified back in 1930s. Over 100 people died in the US alone from DEG poisoning. Since then, regulatory agencies have been responding. The FDA issued a guidance note in 2007. The European Commission allows up to 0.1% DEG from excipient impurities. USP updated its monograph on propylene glycol in 2010, limiting DEG and EG to 0.1%. Despite this safeguard, enforcement and detection remain key challenges, especially in low-resource settings. The World Health Organization (WHO) has included in the International Pharmacopoeia a two-step screening for DEG and EG. During the first step, the samples are screened to quickly identify contamination using a semi-quantitative thin-layer chromatography method. Then, suspected contaminated product may be confirmed by GC. As observed in the International Pharmacopoeia, TLC is already a proven screening method, but when updated to HPTLC, it offers a sensitivity below 0.1%, an accurate quantification, high throughput and reproducibility, and full documentation for traceability. This makes it a powerful tool for rapid screening and semi-quantitative assessment, especially before confirmation by GC. In general, HPTLC is an advancement over traditional TLC with controlled variables, reproducible conditions, and high documentation standard. We use a standardized 20 by 10 HPTLC plate, precise sample and standard application, controlled development, and excellent documentation and visual evidence. The result, HPTLC gives a better precision and robustness than conventional TLC. I will now let Sonia explain you the HPTLC method in detail.
Let's walk through the process for syrup analysis. First, we start by weighing out 1.0 grams of syrup. This is then dissolved in 10 milliliters of methanol. Once it's mixed, we vortex the solution to ensure everything is properly blended. After that, we sonicate the mixture. Next, the sample is centrifuged to separate the solid components. Finally, we collect the clear supernatant, which is what we use for the application or further analysis. Now let's take a look at the materials used in the method. We start with our reference standards These are DEG and EG 1:1 mixtures prepared at the concentrations ranging from 0.025 to 0.1 milligrams per milliliter in 5 different vials. For system suitability, we use the UHM mix. Optionally, include glycerol and polypropylene glycol each at 0.5 mg per milliliter and sorbitol at 1 mg per milliliter, all prepared in methanol. And finally, for the chromatography, we use HPTLC plates, specifically silica gel 60 F254 from Supelco. Now let's move on to the application and development process. Both the syrup samples and reference solutions are applied as 8.0 mm bands with an application volume of 2.0 microliters for both the samples and the standards. For development, we use a solvent mixture of acetone, ammonia, toluene and water in a very specific ratio of 85 to 1 to 5 to 9.5. Before development, the chamber is saturated and we include an activation step for 10 minutes to condition the plates at 33% relative humidity. After development, the plate is first recorded in absorption at 254 nanometers. Next, we carry out derivatization using potassium permanganate, which reacts specifically with glycols. This reaction produces distinct yellow bands on a violet background, making the glycol spots easy to identify. It's important to note that these bands do not appear immediately after spraying. The reaction takes time to fully develop. The plate is recorded 30 minutes after derivatization, this time in white light, reflection and transmission. And finally, when quantification is required, we perform a fluorescence scan at 520 nanometers. The method we are showcasing today is fully described in the application note A148.1 and also published as CBS 134 on our CAMAG website. The results presented here show clear separation between the standards, confirming the specificity of each marker. For example, we see sorbitol on track 2 with an RF of approximately 0.08 and glycerol on track 3 at around 0.37 and polypropylene glycol on track 5 appearing at about 0.61. Our key target, DEG and EG, with a concentration at the set limit of 0.1% are clearly visible on track 4 with an RF value close to 0.53. And now to an example. In the real syrup samples, we see syrup 1 on track 6 and syrup 2 spiked with 0.1% DEG and EG on track 7. In the spiked sample, there is a clear DEG and EG zone at RF 0.53, which perfectly matches the reference, confirming the method's accuracy. From a quality control perspective, this means the sample on track 6 would be considered compliant, while the sample on track 7 would clearly fail due to the presence of DEG and EG. When it comes to the quantification, we use a 5-point calibration curve for the DEG and EG mixture. It starts at 50 nanogram, then continues with 75, 100, 150 and 200 nanogram. Here 200 nanograms corresponds to the 0.1% limit in the sample. What's important to highlight is that even at the lowest level of 50 nanograms, DEG and EG can still be visually detected. That's 4 times lower than the 0.1% threshold, demonstrating the sensitivity of the method. After development and derivatization, we use scanning densitometry at 520 nanometers to generate peak profiles, for which the calibration curve is computed. To generate the calibration curve, we use a linear 2 regression model. The resulting equation, now highlighted, is written in the calibration function, with a correlation coefficient of 0.998, indicating excellent linearity across the tested range. Using VisionCat software, we also calculated the limit of detection and the limit of quantification of DEG and EG. The LOD was determined to be 21 nanograms and the LOQ came out to 46 nanograms, confirming the method's high sensitivity and suitability for trace analysis. Instead of running a full 5-point calibration curve, we can also perform a limit test at 0.1%. In this approach, we apply only the 0.1% reference standard to the plate shown here in the red circle. Along with the point 0, this allows us to generate a simple linear 1 curve. The gray shaded area on the graph highlights the region where samples would be considered non-compliant. With this setup, we can visually assess whether a sample exceeds 0.1% threshold. And in this case, we can clearly see that 2 of the samples exceed the limit, meaning they are non-compliant. And now Tine will take over.
Thank you, Sonia. We see now how HPTLC plates are visually powerful and how each plate tells a story. Yellow zone together with the RF value indicate the presence of DEG and EG, while intensity indicates the quantity. In one glance, we assess both presence and compliance. To summarize, this approach is not only effective, it is a practical solution. It is fast and cost efficient, there is no carryover, you have a parallel analysis fully documented, it is pharmacopoeia compliance, and it's great for quality control or research and development. An additional consideration is the use of a system suitability test to ensure robustness. It is crucial for quality control. For that, you have the universal HPTLC mix, also called UHM, which can be used. Using this method, the UHM will display 4 zones at RF 0.19, 0.53, 0.61, and 0.77. Reproducible fingerprint of the UHM will confirm that your system is working properly. This method is especially useful in low and middle income countries. It's quick, compliant, and gives visual and quantitative assurance, perfect for raw material screening, routine quality control, and regulatory submission. We hope this method empowers more labs to improve syrup product safety. Thank you for your attention. We are now happy to take your question, whether it's about the method, implementation, or specific case scenarios. Please drop them in the chat or use the Q&A panel.